Hi, welcome to Meek Electronics.
Welcome back to Meek Electronics, where we make complex circuits simple and accessible. In today's video, we're diving into the simulation of a classic analog design, the Sallen key low-pass filter. We'll be building and analyzing two versions of this filter, using Proteus and Altium Designer, comparing how each platform handles the simulation process. From schematic setup to output analysis, we'll walk through every step, but we're not stopping at just building the circuits. We'll be comparing frequency response graphs from both tools versus the theoretical calculations, accuracy and fidelity of simulation results, ease of use, how intuitive each software is for circuit design and analysis, simulation speed and responsiveness, graphing and visualization tools, which platform gives you clearer insights, and any quirks or limitations we encounter along the way. Whether you're a student, hobbyist, or professional, this video will help you decide which tool suits your workflow best and give you a deeper understanding of how Sallen key filters behave in practice. Let's jump in and start simulating. Both software packages ran a simple RC low-pass filter with the same component values, and we'll walk through what each plot shows, why small differences appear, and how to tighten up your results. Here we have the two sets of graphs side by side for comparison. Let's go through the comparisons and review them. Both plots display gain, that is V out Vn, across a frequency sweep. Proteus shows this on a dB scale, 0 dB down toward -infinity. Altium uses a linear scale, gain from 1.0 down toward 0.0. Remember, at cutoff the gain is 1 over root 2, approximately 0.707, minus 3 dB. So if Vin is 1 volt, V out approximately 0.707 V, right at the knee. Unity gain. In both tools, the passband is flat at unity. Proteus holds right at 0 dB. Altium sits at a gain of 1.00. This confirms the filter behaves as expected at low frequencies, with no attenuation or peaking. 3. Cutoff frequency, -3 dB point. Next, we spot the -3 dB knee. Proteus's falls at about 1.1 MHz. Altium around 1.3 MHz. The theoretical FC for R equals 150 ohms and C equals 1 nanofarad is 1 over 2 pi RC, approximately 1.06 MHz. So Proteus is within approximately 5% and Altium 20% of theory under their default settings. 4. Roll-off rate. Below the knee, both tools show a classic 20 dB per decade slope, a first-order filter. On the linear plot, this looks like a straight exponential decay. On the dB plot, it's a straight line declining at approximately 20 dB per 10 times frequency. 5. High-frequency floor and noise. At the high end, Proteus bottoms out around 80 dB, which is really the SPICE solver's noise floor under default tolerances. Altium shows a smooth drop towards 0. Its graph simply stops plotting points once they're exceedingly small. 6. Frequency span and resolution. Defaults differ. Proteus swept from 10 Hz up to around 10 MHz with a very fine grid. Altium went 10 Hz to around 100 MHz, but with fewer points per decade. More points give you a smoother curve, but take longer to simulate. 7. Why the small discrepancies? These arise from default solver settings. Step size, points per decade. Fewer points can shift the apparent cutoff. Model interpolation. Each tool's device libraries and default tolerances differ. Noise floor and convergence. Tighter tolerances push the solver to resolve deeper attenuation. 8. How to align and refine. If you want bit-perfect agreement, match sweep ranges, e.g. both 10 Hz to 10 MHz. Set same points decade, e.g. 100 points decade. Toggle scale units, plot both in dB or both linear. Adjust solver tolerances. Lower the absolute error threshold or noise floor. Use identical component models. Import the same SPICE substack if possible. 9. Which is better? Proteus excels in super smooth, high-resolution traces out of the box. Great for visually precise roll-off details. Altium gives a broader sweep range and intuitive linear plots. Handy if you want absolute gain numbers without converting from dB. Ultimately, both deliver the correct physics. The best tool is whichever aligns more closely with your workflow. Whether that's rapid prototyping with default settings, or deep dive filter analysis with custom tolerances. Closing review. In summary, you've got a unity gain, 1.06 MHz cutoff, 20 dB decade RC low pass in both packages. Any small shifts are just default setting quirks. Tweak your sweeps, match units, and you'll see perfect overlap.